right, our next presentation comes from scientific programmer Emily Kahl from the Australian Institute for Bioengineering and Nanotechnology. Emily, how are you today?
Thanks, Brian. Yeah, doing pretty good. Happy to be here.
Yeah, thank you for joining us. Let's get you set up.
Yeah, no worries. Let me just share my screen.
Emily will be presenting the power of scale, unlocking new frontiers in non-equilibrium molecular dynamics with extreme scale compute.
Yep,
And there
can
it
you
is.
see my slides all right?
Absolutely. You're good to go. Thank you, Emily.
All right, sweet. Yeah, so as Brian said, I work as a scientific programmer at the Australian Institute for Bioengineering and Nanotechnology in the computational chemistry group. And I'm going to talk a little bit about the work that we've been doing to develop a bunch of high performance, large scale algorithms for simulating non-equilibrium systems. Now, I'll have to talk a little bit about the science first before I can get to the cool computing stuff. And as it's a fairly complex field of research, this is just going to be like a whistle-stop tour of non-equilibrium statistical mechanics. So there we are. So first we need to talk a little bit about what non-equilibrium systems are and why we should even really care about them. So non-equilibrium in thermodynamics just means that there is a net flux in your system. So there's a flow or a net movement of something like particles or heat or electric charge, that sort of thing. And it turns out that there are a whole bunch of really important systems for industrial applications that are intrinsically non-equilibrium. You need to understand their behavior far from thermodynamic equilibrium to be able to model them properly. So an example that's quite salient at the moment on the left is energy storage technology like batteries and supercapacitors. So as you can see in the little diagram that I have on the left there, we have two electrodes that we apply some potential difference across, and we have an electrolyte in between them. And when we have our potential difference here, that's going to drive a net movement of charge in the electrolyte. And so it's a system that is out of equilibrium. Similarly, we can look at something like fluid flow, for example. So on the right, we have a couple of diagrams. There's an example of simple shear flow, also extensional flow, which is like sort of stretching out the material. And it turns out that there's a whole bunch of materials whose properties can drastically change when they undergo this kind of fluid flow. So examples from this paper that I've taken the diagrams from are polymers. There are a lot of polymers that change, for example, mechanical properties or chemical properties when they undergo shear. So we can do kind of really interesting, specifically targeted manufacturing with it. But also in the natural world, there's some evidence that seems to suggest that maybe spider silk is intrinsically relies on some kind of fluid flow process in order to get its remarkable mechanical properties. And it'd be nice to understand that so we can hopefully duplicate it. We're going to focus in on one particular application here, which is what we're working on with the Pawsey Center. We have a PACER project. It's their extreme scale readiness project to develop these sorts of algorithms. And we're really interested in flow-driven self-assembly of carbon nanostructures. So, for example, look at the diagrams on the right. We've got these nice little tubes, and those are made up of little individual carbon atoms. That's an electron microscope type thing. And these nanostructures, turns out, can have a bunch of potentially really interesting applications in materials science and chemistry. They can sometimes they can potentially, I should say, because this is all very speculative, act as advanced filtration devices. They can be used for really interesting novel electrode design in energy storage technology, and potentially be also used for gas separation in things like hydrocarbons. So really, really cool stuff. But the problem is they're quite difficult to make in large capacities. And often some of these processes that you need to do to make it can result in some kind of nasty chemical byproducts. But there's a bunch of quite intriguing small-scale experimental studies being done somewhat recently that suggest that you might actually be able to some of these nanostructures to spontaneously self-assemble under fluid flow. So if you get the right fluid conditions, a whole bunch of substructures, for example, on the left, tiny little flakes of graphene oxide, so like little sheets of carbon that are a single atom thick, and on the right, buckyballs or fullerenes, which are little spheres of carbon. You put them in some solution, you apply a flow profile to it, you force it through either like a nozzle or you shear it with a sharp piece of metal. And then in the process, all of those things will align or stick together and clump together and form these kinds of cool nanostructures, which would be really neat if we could scale that up because it's a relatively simple process to set up. It doesn't require any sort of chemical intermediaries. But the problem is we've only got small scale experiments to go off. And so we need to know, can we actually get the kind of production rates that are necessary for industrial applications? And that's where we would like to have computational science come in, because we can sort of understand what is driving this flow reaction at a molecular level and hopefully figure out what sort of parameters we can sort of experiment with and tweak in order to increase the reaction rates. But there is a problem, as always, which is that in order to really get to the bottom of this, we're going to need to look at simulations with very large numbers of atoms and also very long timescales, because this is potentially, from a molecular perspective, quite a slow reaction. So that means that it's very computationally intensive. It's a pretty chunky problem. Now, hopefully I've convinced you that this is all important. So let's talk a little bit about how we do the simulation. We use molecular dynamics, which is one of the standard techniques in computational chemistry, where we essentially try to simulate the molecular motion by iteratively solving the classical equations of motion for particles in some finite simulation box. So as you can see, hopefully in the little diagram, the little movie on the right, this is what a molecular dynamics, very simple molecular dynamics simulation looks like. We have a whole bunch of particles moving around, interacting with each other according to some set of forces, and then we just essentially calculate their trajectories, their positions and velocities by solving Newton's equations of motion. We have two coupled ODEs, and we solve those based on the particle forces. We need a good model of these forces, and this can be quite computationally challenging. It's often the most expensive part of any molecular dynamics. This can be things like interatomic forces, like your van der Waals dispersion forces. It can be molecular bonding forces that keep molecules held together. Long-range Coulomb interactions, if you have charged particles, very important for a whole bunch of interesting processes. And of course, any external force to our system, if we are simulating a non-equilibrium system. Once we actually have this done, we'll have a set of trajectories for the particles in the system. And these should hopefully sample a statistical distribution if we've done our calculation right. For example, a microcanonical distribution. We can then link the microscopic motion of our particles through these trajectories and use statistical mechanics to predict the thermodynamic properties that we're interested in. So this could be things like viscosity, heat transfer, reaction rate, all of that sort of stuff. And as a result, we can link our microscopic motion, which we can simulate, to the bulk thermodynamic properties, which are what we actually measure in an experiment. So pretty cool. Move into a little bit further. Oh, and I forgot to say, usually we want to use periodic boundary conditions for this. So that means that when a particle crosses over the outside the boundaries of the box, it pops back in on the other side with the same velocity it had when it left. So if you look at the movie, you can sort of see some particles disappearing off the right-hand side of the screen and popping back in on the left-hand side, and then vice versa. And what this means is that we can, with a little bit of mathematical trickery, eliminate the effects of the finite simulation size that we're limited to for computer simulations and link the properties back to bulk systems, so ones that are very, very large and sort of experimentally realistic sizes. So that's very important, and that will come up later. So now in molecular dynamics, we need to go a little bit step further, because we usually want to fix some combination of temperature, pressure, or volume in order to mimic the sort of experimentals we need to see. And throughout this talk, I'm just going to talk about fixing the temperature to some set amount, say 300 Kelvin or something like that, just for simplicity's sake. And to do that, we use what's called a thermostat. And much like the thermostat in your house, if the temperature of the system gets a little bit too high, it takes a bunch of thermal energy out. And if the temperature is lower than it puts it back in. And it does this by essentially calculating the current temperature of the system, which is related to the total kinetic energy of all the particles inside it. And then it uses this thermostat multiplier, which I've got centered on the right, which is a modification to the equations of motion. There is a lot of detail here that I'm skipping over, and there's numerous different schemes that you can use to thermostat a system. And this is a very complicated system, but the high-level picture I gave you there should suffice for the kind of stuff that we're dealing with. So now let's talk a little bit about fluid flow. In particular, we're going to focus on shear flow in this talk, although a lot of this stuff is equally applicable to extensional flow, so stretching and that sort of stuff. And there's two kind of ways that we can think about simulating fluid flow in molecular dynamics. The first is using the boundary conditions of the simulation itself to drive it. So if we have our diagram on the left here, we have some fluid that is confined between a couple of walls. You can see this being anything. There could be glass, there could be, sheets of graphene, who knows what. The important thing is that there is an interaction between the wall atoms and the fluid atoms. We only have periodic boundary conditions in the X direction here, and we fix things in the Y direction. And then what we do is we force the wall atoms to move in opposite directions. So in this diagram, the top wall atoms move in the left direction, negative X direction, and the bottom ones move in the positive X direction. And the interactions between the wall atoms and the fluid atoms cause the fluid near the surface to get kind of dragged along by the wall. And the net result of this is that you get this nice linear sort of shearing profile in between the two. Very cool. However, this requires us to abandon our periodic boundary conditions in one direction, which we kind of don't want to do if we want to look at bulk systems. It's useful for nano-confined fluids in like very, very tiny, nanoscale channels, but that's not what we're looking at simulating in this particular project. So we need something to be able to simulate homogeneous shear flow as shown on the right. So here we're back to our periodic boundary conditions in all three sort of coordinate directions. And we want to apply this linear streaming profile so that the velocity, the sort of flow velocity of the atoms, which will be superimposed on top of their random thermal motion, which gives us the temperature, changes linearly as a function of one or more axes. Traditionally for this thing, we'll just take the y-axis to be the direction that we are changing it in. So in order to do that, we use a thing called the Slog equations of motion. So Slog describes the fluid flow of a homogeneous bulk fluid undergoing, could be shear flow, could be extensional flow, could be some mixture of the others, but we'll focus on shear flow for this. And it is driven by a synthetic external field. So it's not driven by the boundary conditions of the simulation. And this is really important if we want to be able to link our thermodynamic properties that we get from it to things that we could see in, very large systems. So we also want to thermostat it, which we can see in our multiplier to the right. And the things that I've circled, those are the terms that give us our velocity flow profile. To get a little bit more concrete, when we're dealing with planar shear flow, which is this thing diagram on the right again, that just reduces down to some constant factor, which we call our strain rate, multiplied by the position and momenta respectively in the y direction. So they are relatively simple to write down, but there's a lot of subtleties in how you actually solve this stuff. And that's where the bulk of this project comes from. One such subtlety that's quite important is that you need to have the correct periodic boundary conditions for your simulation in order to make sure that your boundary conditions don't impose extra forces on the molecular motion. So the way we do that, or one of the ways we do that, and the way that turns out to be the most computationally efficient, is that we let the simulation box deform under time. We make sure that the vectors that make up our simulation box actually evolve under the same equations of motion, the same flow profile as the particles. And this means that we end up having simulation boxes that go from nice cubes and then tilt slightly and get this sort of triclinic box as it goes. And this ensures that when a particle pops out the top of the box and it comes back in the bottom, it ends up the correct flow profile for the bottom of the box. And it means that we have our nice equivalent to a bulk system. Also, we want to thermostat this because, again, we want to keep a fixed temperature. And in particular, this external field is going to do work on the system, which we're going to want to wick out so that it stops it from heating up. Now, there's two ways we can do this. We need to calculate the temperature using the kinetic energy, which we get from the translational momentum of the particles. But there is actually a little bit of freedom as to how we actually calculate that. We can either use the individual momenta of each atom in the simulation, which is the little bottom left diagram, or we can use the center of mass of the molecules and get the translational momentum of that in order to calculate what we call the molecular temperature. Now, it turns out that in an equilibrium system, these should both converge to the same thing. However, in a non-equilibrium system, it's really important to choose the correct one. And it turns out that, as you can see in the diagram on the right, when you have a molecule in this sort of flow field, it's going to tend to want to rotate in line with, and the atomic thermostat because of the way it works, it doesn't know anything about molecular momentum. And so it ends up actually trying to restrict that. And it applies an artificial torque to the molecules in your simulation, which is unphysical, and it causes them to sort of line up in this sort of shear-driven alignment that's actually fictitious. And this can result in completely wrong dynamic behavior of your system. So we really need to use the molecular temperature when calculating this stuff. So that's the science. Hopefully that was all good. Thank you for bearing with me so far. Now let's talk about the computing. We have been using the LAMMPS molecular dynamics software package, which is one of the more widely used open source molecular dynamics codes maintained by some of the Department of Energy labs in the United States. It's written in modern C++, crucially with modular design patterns. So it's designed to be easy to modify and extend via what it calls packages and styles. So if you're writing your own code, ideally, you don't have to touch much of LAMMP. A few extra things, add some extra compile options, and Bob's your uncle. It'll just run, which is really handy. It's also designed to run at scale. It's got PI parallel threading and also GPU parallel, because we need to spread our calculations across multiple GPUs, ideally a lot of GPUs, in order to be able to get the kind of compute rate that we need to simulate these really large systems. There's also another benefit here, which is why we've chosen LAMMPS, which is because it is so popular and it has so many user bases and it's so easy to contribute to, it means that it is a much higher return on our development investment to modify LAMMPS, so to add some of these non-equilibrium routines and then contribute it back upstream, than to write and release our own program. If we modify the LAMMPS and get it included back in the main distribution, then all of the changes that we've made are now available to everyone who uses LAMMPS, which at the last estimate that they made was sort of over 10,000 users, which is quite nice. And so we have this PACER project now to develop non-equilibrium molecular dynamics packages for these kinds of calculations in LAMMPS, and to make sure that the science is really good and easily available to everyone who wants to use it. Now, with GPUs, we have decided to go with the COCOS framework for doing heterogeneous compute offloading. And the reason for this is that there is a whole zoo of GPU architecture, as I'm sure you're all familiar with, AMD, NVIDIA, now Intel entering into the market, as well as potentially wanting to do CPU-based calculations as well. And the appeal of COCOS and why it has been included in LAMMPS is that it is a framework written in modern C++ that essentially lets you outline the high-level details of your algorithm, how you want to dispatch the parallel work, what sort of execution policy you want to have, how it should move between host and device, and then let the compiler deal with a lot of the vendor-specific boilerplate. So it's written in a high-level modern C++ and makes very heavy use of template metaprogramming to be able to handle this. And it also has very robust support in LAMMPS. LAMMPS has a COCOS package as well as a more traditional CUDA/HIP package, but the COCOS one is under pretty active development, and it already has a whole bunch of really nice LAMMPS features built into it, which means starting from the ground up when we do this. And hopefully we should be able to target both the NVIDIA GPUs that we already use in our group and the upcoming AMD GPUs at Pawsey when we run these large-scale calculations without having to write multiple bits of code for each. You just change a compiler flag and away you go, or at least that's the idea. So what does COCOS look like? Here's a brief overview. Here's some functions that I wrote a year ago to actually get some of this. This is for long-range Coulomb interactions in these sort of shifting boundary conditions that we need. So on the left, we have our compute kernel. So you can see that it's a templated function based on the device type. So that will be instantiated at compile time, whether we want to give it a CUDA or a HIP GPU or OpenMP for CPU parallelism. And then we write our function, which actually looks pretty similar to what you would do in something like a CUDA kernel. And then on the right is how we actually call that from code. So again, we have to have a templated function so that it gets passed through properly, but then we just give it our execution policy, which in this case is a parallel for loop. We tell it what the ranges to our for loop are, and we tell it which function we want to execute. In this case, it's our compute kernel on the left. And then COCOS will generate all of the correct device-specific code to actually translate that into your CUDA execution call or your HIP kernel dispatch for you, which is very nice. So it just looks like modern C++, and it's relatively easy to write for people who have experience with C++, but not necessarily experience with GPU-specific programming. We found in our group that when getting people to do collaborative development with us for this, it's has a relatively plain CUDA or HIP, which is an advantage when we're dealing with quite a diverse research group. So the LAMMPS CoCos package is the newer of the two, and it's important because GPUs have changed quite a bit in the last few years, and in particular, compute power has continued to massively exceed bandwidth between host and device, which means that it's quite important to keep all of your data on the device for as long as possible. You want to minimize those transfers because they will become the bottleneck if you have too many of them. This was not the case for the earlier GPU packages, which were designed to try and overlap GPU and CPU compute, but that's becoming sort of less appealing as GPUs get more and more powerful and bandwidth gets worse and worse. So we're going to stick with CoCos. There were no non-equilibrium molecular dynamics compiles when we had this project at the end of 2020, beginning of 2021, so we had to write some. So first we did atomic slot, which, while not useful directly for the kind of systems we want to simulate because it uses an atomic thermostat, it was enough to provide a sort of test case for making sure that we got our, at least the variables, which it can. So we wrote CoCos accelerated subroutines to do the slot equations of motion, to handle the compatible periodic boundary conditions, those sort of shifting triclinic boxes, as well as long-range Coulomb forces in the non-cubic simulation geometries, and support for fast Fourier transforms, which are used in the long-range Coulomb calculation on AMD. Code is now back into the upstream code base. It's ready to go. If you download LAMMPS right now, you can get cracking. And our postdoc, Stephen, has also fixed some sort of miscellaneous errors in some of their numerical algorithms, which we have a patch pending for. So keep an eye out for that if you're interested in this kind of thing. So we have some timing diagrams or some timing tables on the right, and we can see that we get, nice performance on the GPUs. It's compared to the old Magnus CPU cluster at Pawsey, we have pretty fast runtimes on the V100s and MI100 GPUs. There are a couple of problems with this. The performance is not as great as I would like just yet. In particular, our multi-GPU performance is a little bit, there's a few things to work out there. And also we can see that our performance on the AMD MI100 GPUs is a fair bit slower than the V100 GPUs, despite on paper, they should have similar sort of performance. And this is what you see with, say, AMD's vendor supplied benchmarks. And we're still trying to work out what that is, but we think it's somewhere in the long-range Coulomb interactions. And we'd like to get that fixed so that we can actually get as much performance out of these AMD GPUs as we need. In addition, we have done some work to add these molecular slot algorithms into LAMMPS. And this was actually a pretty non-trivial development problem because LAMMPS was designed as a particle simulator first and foremost. The molecular framework is sort of bolted onto the top and not really integrated with the core routines, which means that we're trying to force this molecular formalism into the code to make it do something that it was never really designed to do from the ground up. So we did the bulk of the coding for this during a code sprint with Pawsey and also Fluid Numerics in the United States. And we added a bunch of new molecules to track molecular properties and to simplify some of the bookkeeping to centralize everything. This meant that we could now add a molecular thermostat, which means we can correctly calculate the trajectories of molecular systems under shear flow, also the molecular slot equations of motions, as well as a few physical properties that are useful for diagnostics to make sure that our algorithms are correct. So this is what took the bulk of this year. The code works on CPUs with MPI parallelism, which is a good start. And we're working on the CoCos port now, but we need to sort of make sure that we have all of our physics correct before we sort of jump in guns blazing. However, I am pretty sure that before too long, we will have that up and running, and then we'll be able to finally do these really large-scale molecular fluid flow calculations on really, really big systems. So we have some preliminary results that are kind of cool looking. This little movie on the right is a set of 3 graphene flakes in some water undergoing this shear flow. It'll be really interesting to test this with much larger molecular systems because, as you can see, they seem to have some degree of alignment, but it's not clear whether that's actually real or an artifact of some simulation stuff. And Ultimately, we would like to merge this molecular slod stuff back into the main LAMPS code base so that it's available for everyone to use. So with that, I'd like to thank my colleagues at Bernhard Group, my boss Deborah, and my colleagues Stephen, Sharon, Charlotte, and Amy, who have done a tremendous job with getting the physics actually worked out and ready to code. I'd like to thank our technical collaborators, Marco at Pawsey Center and Joe at Fluid Numerics, for their help during the code sprint itself. Also, our scientific collaborators, Peter and Billy. They've been fantastic with helping us and answering all of the questions we have regarding molecular fluid flow. And of course, the generous people who have provided us with computational resources. And with that, I'd like to say thank you and open the floor to questions.
Emily, thank you very much for the presentation. That was fantastic.